Welcome to Engineering Chemistry Lab videos. Myself, Dr. Kiran Kumar P, Assistant Professor at ATME College of Engineering, Mysuru. Today's experiment is all about the estimation of copper colorimetrically. So colorimeter is an instrument. It is a qualitative analytical technique used for measuring the transmittance or absorbance of a light passing through the colored solution. So generally, colorimeter is an instrument used to measure the concentration of colored solution. So by measuring transmittance and absorbance, we measure the concentration. So colorimeter is mainly based on two fundamental laws of absorption. One is the Beer law, another one is the Lambert's law. Where the Beer's law states that when a monochromatic light is passed through the colored solution of constant path length, remember of constant path length, the absorption of light is directly proportional to the concentration of the solution. For example, here we have two different concentrations placed at the same path length. So this is the path length where light has to be traveled, right? So all these different concentrations of C1, C2 and C3 have the same path length, right? Now, when a monochromatic light is incident on these colored solutions which travel along the same path length, when light is incident on this colored solution, there will be three processes, right? One is the absorption. There will be some absorption of light due to the colored solution. Some may be transmitted and some may be reflected. So in general, the reflected light will be negligible, right, for glass. So in Beer's law, when a monochromatic light is passed in a different colored concentrated solution of same path length, so there will be the absorbance is directly proportional to concentration. So here you can see the C3 concentration is lesser than C2 than C1. So C1 has higher concentration. So here in C3 there will be less absorbance but more transmittance. Transmitted light will be more here due to lesser concentration. Whereas in C2 there will be more absorbance than C3 concentration due to high concentrated solution and less transmittance. Whereas in C1 there will be more absorbance but lesser transmittance, right? So this is what the Beer-Lambert's law is, right? I repeat, Beer's law is when a monochromatic light is passed through the colored solution of same path length, of constant path length, the absorbance is directly proportional to the concentration. If more is the concentration, greater will be the absorbance. Absorbance of what? Absorbance of light. Similarly, this is what it is. It can be represented as absorbance A is directly proportional to concentration when path length is kept constant. Whereas in Lambert's law, it states that when a monochromatic light is passed through the colored solution of constant concentration, so here we are talking about constant concentration, the absorption of light is directly proportional to the path length. So in Lambert's law, the path length is varied. You can see L3 has higher distance of light to be traveled when compared to L2 and L1. So in this case, so we have three same concentration of different path length, right? When a monochromatic light is passed on three different path length of same concentration, here in L1 there will be less absorbance due to less path length, am I right? Whereas in L3 there will be more absorbance but less transmittance due to light needs to travel more distance, right? So this is about Lambert's law. So Lambert law states that when a monochromatic light is passed through the colored solution of different path length, so this absorbance will be directly proportional to path length, right? So here, if concentration is more, absorbance will be more and path length is kept constant, whereas in Lambert law, absorbance will be more when path length is greater, when concentration is kept constant. So, in order to calculate the absorbance, there is a combined law, we call it as Beer-Lambert law, where it states that when a monochromatic light is passed through the colored solution of constant path length, the absorbance will be directly proportional to concentration. It is given by A is equal to epsilon Ct, where A is absorbance, epsilon is molar absorption coefficient, or which is a constant, C is the concentration, T is the path length. So according to this equation, when path length is kept constant, A will be equal to C, right? A is directly proportional to C. So the absorbance of a colored solution will be measured at a particular lambda max. So it varies with different solution of color. Now let us see instrumentation part for colorimetric estimation of copper. The colorimeter is a photoelectric colorimeter. It is also called as photoelectric colorimeter, which consists of a light source of 400 to 750 nanometer, a monochromator to monochromate a light, a sample cell to keep the path, sample cell to keep the sample, photocell detector which detects the transmitted light and converts it into an electrical signal. It also has a digital meter which records the digital reading. So this is a typical instrumentation part: light source, monochromator, sample holder, photocell detector, and a digital display. So the working is when a light of wavelength 400 to 750 nanometer, that is the lambda max, required lambda max, is incident on a monochromator to give a lambda max desired wavelength. Then it is passed in a colored solution where some light gets absorbed, some light gets transmitted. So here the transmitted light is identified by photocell detector and we get a direct digital display. It may be in terms of transmittance or also we can record the reading in terms of absorbance. So this is a experimental demonstration. So this is a typical colorimeter instrument. We have a filter. So this filter ranges from 400 to 700 nanometer visible region. So this is a knob to adjust the absorbance or transmittance. So this is a cuvette to place the sample, right? So this is a digital reading. It may be recorded in terms of transmittance or absorbance. So this is a typical digital colorimeter. So in order to do the experiment, you need the standard flask. Here we go. 5, 10, 15, 20. We need copper sulfate, which is filled in a burette. We need ammonia solution and water. So two different standard flasks. Take 5, 10, 15, 20 ml of given copper sulfate solution. So initially I am adding 20 ml first. 20 ml of copper sulfate is added. Now 15 ml of copper sulfate is added to different standard flask. Now 10 ml. Now 5 ml. Similarly, there will be an unknown solution which will be given to you. You need to take that one also. For each of the flask, add 5 ml of ammonia. 5 ml of ammonia is added to each flask. 5, again 5 ml for this solution, 10 ml of copper sulfate, again 5 ml for 15 ml of copper sulfate, again 5 ml for 20 ml of copper sulfate. So these are your solutions now. So to this solution, add water. So this will be a blank solution where only 5 ml of ammonia is added, but not copper sulfate. We call it as blank solution. So these are your solutions. Now to each of a solution, distilled water is added up to the mark and need to mix the solution well for uniform concentration. Add water, distilled water up to the mark here, up to this knob. Should be very careful. Should make up the solution exactly to this mark. Should not overfill. So hence, in order to avoid overfill, you need to add water up to this neck. So the remaining water is added through the burette. Right? So remaining water up to this mark is added carefully by the help of burette. Once you get the mark, mix the solution well, invert the flask for multiple times, mix the solution well for uniform concentration. This is a very important step. You need to mix the solution well to get uniform concentration. Do this step for entire flask for 5, 10, 15, 20 and for even your blank solution. Right? Now you got your standard solution of different concentrated copper sulfate. Now the same procedure is done for the blank, for the unknown sample, where the copper sulfate is given to you and you need to add ammonia and make up the solution. Now take the blank solution where copper sulfate is not present here, fill it to the cuvette. Wipe using the tissue paper, place it into the sample holder, and since it is a blank, right, the absorbance, it should be 0. So press this button or to get absorbance and adjust using the knob to set it as 0. Why? You don't have any sample here, it should be 0. Now, in the similar way, take 5 ml copper sulfate solution, wash with, for initially rinse with 5 ml, the same solution, then transfer again Now remove this one and wash and wipe using tissue paper. This process is done in order to avoid the reflection process, to ensure maximum absorbance of the colored solution. Immerse the cuvette. Now record the reading. It is in the form of absorbance, right? 0.09. So this value is for the copper sulfate of 5 ml. Now, so in the similar manner, for each of your standard solution, you need to note down the absorbance. But remember, to measure the absorbance of different flask, it should be recorded with respect to the blank. Remember, in each trial, you need to keep the blank cuvette and make sure the absorbance value is 0, right? Once it is done, again for blank solution, ensure it is for 0, then take the unknown sample. So this is the unknown sample where you don't know how much copper sulfate is added to this flask, okay? Now for unknown solution also record the absorbance value. It's 0.17. So let us see the procedure with a demonstration. Draw out 5, 10, 15, 20 ml of copper sulfate to each standard flask. Now add 5 ml of ammonia to each of the flask and mix the solution well. Add water, make up the solution up to the mark. For even test solution, you should add ammonia and make up the solution. So this is what it happens. You have copper sulfate, you are adding ammonia, it forms a complex of cuprammonium sulfate. We call it as cuprammonium sulfate, and the color of this complex is deep blue color. You can see here there is a very mild difference in concentration, even it has 20 ml of copper sulfate. But after adding ammonia to each of a solution, you can see the difference here. This has shown darker or more deeper blue color, right? So now thus this has more concentration of copper and this has less concentration of copper. If the light passes through each of a solution, obviously this flask which has 20 ml of copper sulfate shows greater absorbance, right? And blank which doesn't have any copper sulfate, it's clear, hence the absorbance is set as 0. Okay, now so this is a colorimeter. You need to measure the absorbance of each of a solution as shown in the previous demonstration with respect to the blank at 620 nanometer. Here the 620 nanometer is the lambda max value, where at this wavelength deep blue colored solution absorbs maximum light radiation. Hence 620 nanometer filter is set. Now on plotting a graph of absorbance, you are measuring absorbance versus the concentration 5, 10, 15, 20. You get a straight line passing from origin because the blank has 0, right? This solution has got some absorbance. If you see that absorbance, that corresponding concentration is the concentration of copper sulfate, that is due to unknown concentration. Okay, so this is how we can calculate the concentration of unknown copper sulfate. I repeat, this is a flask, empty flask. You are adding copper sulfate 5, 10, 15, 20. For blank, it is given to you. You don't know that copper sulfate concentration. You need to calculate it. This is a blank one. This is a test sample, and this is a blank one. You are adding ammonia to each of a solution. This is what the reaction. Cuprammonium sulfate on adding ammonia. It forms a complex of deep blue color. Make up the solution. Measure the absorbance using colorimeter with respect to the blank. And plot a graph of absorbance versus concentration. You can calculate the concentration of given test sample. Right? This test sample. So this is what the experimental observation is. 0, 5, 10, 15, 20, 25 ml of copper sulfate. Weight of copper, absorbance at 620 nanometer. So for 0, it's 0 for blank, right? B will be given for you. B need to be calculated with the help of A. Concentration of copper sulfate in 1 cm cube of stock solution. It is given to you. Using this A value, you need to calculate B, right? Now, volume of copper sulfate in test solution Y is equal to test solution I am talking about, right? It can be calculated from graph. This Y into B, right? That you will be writing here. Weight of copper sulfate in test solution. Y volume into B. B is calculated here. And volume of test sample is also noted here. Y is noted here. So this is about the experimental calculation. Thank you.